Hi, welcome to this recording concerning two important theorems in mathematics that we really need for our class. So I'm going to start with them. And those concepts have to do with the divergence theorem and also the curl theorem. Okay, these two concepts are related honestly to the fundamental theorem of calculus. The idea is the following. First of all, I'm going to start with the divergence, okay? So the integral of the divergence of a vector, which I'm going to call, let me call the vector A, okay? We're going to be using the letter A extensively for the area. So I'm going to call it the vector B, okay? Not necessarily having to do with the magnetic field, but that's a vector nonetheless, okay? It could be the magnetic field. So we're interested in trying to find the the integral of this over a volume, V, and this, according to the divergence theorem, is nothing but equal to the flux of this vector B over the surface that encompasses, that surrounds that volume V. So this surface, symbolically, we write it as partial V, meaning it encloses V. That's basically what that means. Imagine you have a basketball, for example. It doesn't have to be fully inflated. It could be partially. So it doesn't have to have a regular shape. In other words, that you're interested trying to find what is the value of this quantity, which is a divergence of this vector B inside that shape. Then what you do in this case, you can just focus on the skin of that shape, namely in the case of basketball, the skin of the basketball, and just compute there the flux of that vector B over that closed surface. That's what that circle means, it's a closed surface. So this is the divergence theorem that I need to come back to. And also another theorem that we're going to discuss today is the one that has to do with the curl. So imagine you're trying to find the value of the curl of a vector B. This is how we write the curl of a vector B on a surface. In this case, it does not have to be closed, it could be open, and actually the idea it has to be open is that it is equal to the path integral of this same vector B as it circulates over the contour only of that surface, namely on a path integral. So that path, so this surface is S in here that we are interested in to find the flux, if you wish, of the curl of that vector B. And that is equal to basically the path integral over a path L that also symbolically we write it as partial S. In this case, it's a path that goes around, if you wish, surrounds the area S. Okay, so that's basically what this whole business of curl is. So this is, I'm going to refer to as the curl integral. By the way, there is a version of this theorem that is actually an n-dimensional case, but I'm not going to go into it because most of the times those are the cases we're interested in physics. So those are three-dimensional cases. So you have a volume integral in space now, and this boils down to a surface integral over the surface that surrounds that volume in space. And the same thing, you have in this case a surface integral in space also. So the shape in here could be any arbitrary shape. This is the path integral, again a path in space. Of course, you have to have space in here, although you're doing at most two-dimensional integral. Because of the fact that curl is only defined in 3 dimensions. You can't define a curl in 2D or even in 4D. So the only valid definition for the curl, the cross product in general, not just necessarily the curl, is actually in 3D. So this is, as I was saying, related to the fundamental theorem. Imagine if I have a function f of x that is happen to be the derivative. So this is a 1D case, okay? The derivative of the function f of x, then this ensues that the integral over a path over a region on the x-axis between a and b of f of x dx is simply equal to f of b minus f of a. I wanted to draw this comparison in here with the 1D case, because what we have in here, we have one integral being converted to no integral, clearly to a plane area, okay, which is just these areas that is between the x-axis and this values in here, okay. And to the two-dimensional version, basically, where you take a two double integral, you convert it to a single integral. Granted, this is a surface integral and this is the path integral. This is a special kind of a one-dimensional integral. This is actually called a path integral, especially with this circle in here. That means it's a closed path. Your starting point is your ending point, okay? Whereas in this case in here, you have a triple integral basically in space. You convert it to a double integral. And again, this is a special classification of double integrals. Double integrals can be closed or open. In general, they can be whatever shape you like. But this is a special class of those types, namely over a closed surface, okay, not an open surface. So this is basically the idea behind it. And that closed surface has to enclose that volume B that we're talking about. Again, we're going to need this down the road when we convert Maxwell's equations from their integral form down to their differential form, because it's much easier to work with differential equations than with integral equations. So let me give the rationale for this one, and I'm going to follow the analysis by Feynman in his lectures. So please, if you want to, you can explore the idea further in his lectures, which is available for free online, by the way. So imagine we have a surface in here. Oops, what happened in here? Imagine we have a surface in here, okay, of arbitrary shape. But the key thing in here is that this is a closed surface. It's not open. So in other words, there is inside of it a volume V, okay? And I am interested trying to find what in the world is the value of this vector B. Did I change the notation down the road? No. Okay, what is the value of the flux of this vector B over this closed surface S? So this is the surface S and it's closed. That's what this means, okay? And I'm trying to find what the flux of that vector is. So this is what I'm going to do. Instead of doing this integral, I'm going to divide it into two pieces. Instead of calculating the surface integral over this closed surface, I'm going to divide that closed surface into two closed surfaces by coming anywhere and making an arbitrary cut. It doesn't have to be straight, but straight would help a little bit, okay? So imagine you have a basketball and you cut it smack in the middle, and then where you made the cut, you don't leave it open. You actually patch it with other surface in here. With two surfaces on one side and another one on the side, and you will have like two domes basically, and both of them are covered from top to bottom, so there is no air that comes in and out, so it's still sealed if you wish. So the two halves are still sealed. And now what I'm going to argue is that the closed this integral, the flux over this big area S, is just the sum of this over these two surfaces, namely S1 and S2. So S1 and S2 are still closed, okay? So that you know, when I made the cut, I put back, if you wish, I close them again. So I'm trying to find the value of this over these two surfaces, adding them together, and we'll see that it is equal to that one. So for that, let me change the color quickly. For that, I'm going to imagine in here that there is a patch of surface, okay? Part of that where I made the cut, okay? And that, of course, has the same area whether I'm looking at it from S1 side or from S2 side, but the orientation is not necessarily the same. We're going to follow the right-hand rule, and we're going to say for surface S1 is going to point in this direction, which I'm going to call N1 hat, okay? And for surface S2 is going to point in the opposite direction, N2 hat. Those are the two surfaces. Having said that, the vector itself, B, is a given vector in that location. So since the area is small enough, so I can assume that the vector B is the same everywhere in here, and this is the vector B in here in this region. Obviously, I'm trying to find what in the world is, so this area has a size delta S, okay? It can be infinitesimal if you like, okay? And its orientation is N1 on this side, so this is delta S1, and on the other side, the other area in there, it's gonna be delta S2, whose orientation is given by delta n2 hat. Okay, those are unit vectors only. So the key thing in here to note is the following. This angle made between the vector b and n1 hat, let's call it theta. The angle made between n2 and b2 hat is 180 degrees subtracted from theta. So this is pi minus theta. So what that means is the dot product of the vector b with the area delta S1 is going to be equal, of course, b times the size of the area times, which is delta S, both of them. So I'm going to assume that delta S1 and delta S2 are the same size of the size delta S, okay? Ultimately, this quantity is going to go infinitesimal small, okay, when we sum up. So it doesn't matter. So it's going to go very small and we're going to integrate at some point. So this area in the patch that I took it kind of big, but at the end, we're going to make it small so that we can sum up through everything, okay? So it's going to be ds anyway. So anyway, times cosine of theta. That's what the dot product is. Whereas for the same value times the second area delta S2 is going to be the same b times the same delta S, the same size of areas, times cosine of 180 degrees minus theta. Well, this is negative cosine theta. That's trig identity. Okay, that's a negative cosine theta. We know that. So the two quantities are the same numerically, but one of them is opposite in sign to the other. So if we add this quantity side by side, the contribution from the side of S1 on where we made the cut and the contribution from S2 where we made the cut, they cancel one another. Okay? So in other words, this integral in here is going to be for S1 is going to be just the rest of the S1 without where we made the cut. And the contribution from S2 is where everywhere except where we made the cut. So in other words, when we add them together, they really give me the integral over the entire area, because that's exactly what it is. The entire area is just this portion plus the other portion without where we made the cut. And this, where we made the cut, it cancels out anyway because of the property of the dot product. So because of that, then I can go willy-nilly and start cutting this surface to whatever shapes we want to. As a matter of fact, I'm going to take S1 and cut it into two different portions. On the top one, I'm going to call it S11, and the bottom one is S12. And then keep on doing this until basically I arrive to a small enough quantity so that I can do the calculations. S112, for example, will be divided into S1 121 and S1 122 and so on and so forth. So imagine that I go everywhere the areas match, they will cancel out until at the end I arrive to the outer edge of the surface, which is what I want to do all along. That does not cancel because it doesn't have outside region for it to cancel. That's really our starting point. So this is what I'm going to do then. I'm going to keep on cutting and cutting and cutting until I arrive to a place where I can do the calculations actually, and then start from there. So imagine we arrive to a point in space, x, y, and z. Those are the Cartesian coordinates of that space. And of a width delta x, we're going to have x plus delta x, y, and z. And then on a height of delta y, the point is going to shift to y plus delta y, and everything stays the same. And then we go in a depth into the screen in here by an amount delta z. So this is going to be x plus delta x, y plus delta y, and z plus delta z. Okay, obviously, I'm going to finish this shape in here. It's going to be a cube, of course. In space. Oops, up to here only, sorry. So this is my cube in here. Let me see if I can get my drawing tool in here. Lasso tool. Delete that part. Actually, delete this one too. Okay, so basically this is the shape where we are going to just find, namely, we're still after b times our delta s, where s now has 6 faces. You have 2 in the x direction, 2 in the y direction, and 2 in the z direction, in and out of the screen. So the 2 in the x direction are pointing in the I hat direction, and pointing in the negative I hat direction, and the two facing in the y direction, one of them is pointing in the j hat direction, the other one in the bottom is pointing to the negative j hat direction. There is one that is coming out of the screen towards me, and that is in the k hat direction, and there is another one pointing into the screen, and that is a negative k hat direction. The sizes of these areas. The area in the x pointing in the positive x direction has a height delta y and a width delta z. So this area here has a magnitude of delta y delta z. The magnitude of this area also has a height of delta y and a width of delta z. So this one also has a magnitude of delta y delta z. That is in the x direction. In the y direction, so that you know, has a width of delta x and a depth of delta z. So this area has a delta y delta z, and so is this one too, has a width of delta x and a depth, delta x. It has a width of delta x and a depth of delta z. This one has a width of delta x and a depth of delta z. So this area in the bottom is also delta x, delta z, and the area that is facing me has a height of delta y and a width of delta x. So when I'm doing this product in here, I have to be careful with it, and that's it. So this is equal to B, the x component of B, because remember, this is a dot product. So this is a dot product, Bx delta Sx and By delta Sy, and so on and so forth. But I have to pay attention to which side of delta x we're talking about in here. So there is a contribution from this area, which is positive because the vector B and the area are in the same direction. At least Bx is the x component pointing in the I hat direction, and delta and the area in this case is actually pointing in the negative direction. Okay, so having said that, the value of the vector B in here is everything is the same except x is shifted by an x plus delta x. So it's going to be the x component of the vector evaluated at x plus delta x and y and z minus. So I took already the size of the area because this size of the area and this size of the area are identical. So I took it out as a common factor times the same value of the vector bx because it's pointing, the area is pointing in the opposite direction. And this is evaluated at x, y, and z. Times the size of the area, which is delta y, delta z. Okay. Imagine we can do the same thing for the x, for the y component, because this is not complete sum. This is not complete dot product. So I'm going to add to it by, the y component, because the y component is pointing in the j hat direction, and that is also evaluated at y plus delta y versus where y is. So the positive direction is y plus delta y, and the negative direction is just y. So again, by x doesn't change. So if you're worried in here, oh, this is x plus delta x, so is this one x plus delta x. Forgot the delta in here. Okay, so nothing happened to z, nothing happened to x. It's the same thing. Nothing happened to x, nothing happened to z from this point to this point. This point I didn't write its value, but its value in here is x, and its y is y plus delta y, and its z is z. So this point in here shifts by that amount. So the only thing that varies in the vertical direction is y, from y to the y plus delta y. So everything stays the same. Now it's y plus delta y, and z minus, again, the y component, because we're dealing with the vector b, its y component, but the area is pointing down, and its size is delta x, delta z. So both areas are delta x, delta z. So in here, this one is evaluated at x, y, and z. And this is the size of the area is delta x, delta z. Okay, the last quantity that I want to find is the in and out screen. The ones into the screen and out of the screen. The one out of the screen is located at this point in here, x plus delta x, y plus delta y, z plus delta z. So z has shifted from its original value. Everything else stays the same, but it's pointing into the positive direction. Again, it's the z component of the vector b. So it's going to be plus bz evaluated at whatever x was, whatever y was, but z has shifted to a new value minus the same component evaluated at x, y, and z. Okay? times the size of the area. And the size of the area, you can clearly see the width delta x and a height delta y. So this area is delta y delta z. Okay? No, I'm sorry. Delta x, probably didn't write its value in here, but its width is delta x and its height is delta y. So this is delta x delta y. Okay, so we're in shape. We're in good shape now. We're going to use Taylor expansion. The Taylor expansion says that basically, let's write it down. A function of multivariables x, y, and z is, let's focus on the x component, is equal to plus delta x, I'm sorry, in here. So it's going to be equal to fxyz plus the partial derivative of f with respect to x. That's a 1 that has been shifted by an amount delta x, evaluated at x, y, and z, times delta x plus higher order in terms of delta x squared, which I'm going to make them 0. And the reason why we don't care for the higher order, because ultimately delta x and delta y and delta z are going to go to 0. So the only quantities that remain are of the first order, so that we can integrate over them. So this whole thing is just the difference between the value evaluated at x plus delta x and the value evaluated at x. So that's just the derivative. That's just this term. So this product of b delta s boils down then to the partial derivative of bx with respect to x. This thing, the difference between these quantities in here. This is just the extended version of the one-dimensional definition of the derivative, which is the partial derivative, that's all. Of course, times delta x, because that's what the term is. That's the leading term in Taylor. So that's going to be delta x. But then I have also delta y delta z from the area. Delta y delta z. Okay, plus the second term is with respect to y, but it's the y component. So it's the derivative of by with respect to y times a delta y that I need to pick from this difference, but I already have delta x delta z. I'm sorry, I'm looking at this term. So I'm going to pick up a delta y in here, but I already have delta x delta z. So I'm going to have delta y times the size of the area, which is delta x delta z. And now the last term in here, bz, the z's component, has the z shifted by z plus delta z. So that's going to pick up the first derivative plus the first derivative of bz with respect to z. And now I'm going to pick up a delta z because of the fact this is coming from this differential form in here, times delta x delta y. Okay. Delta x, delta y, delta z are going to go to 0, and we will end up basically with summing this quantity over all the elements ds, delta s, so that's going to convert into a double integral because this is a circular integral, whereas this one, if I'm summing through delta x, delta y, delta z, I'm summing through a product, which is dv, which is dx, dy, dz in Cartesian coordinates, okay? And therefore I'm doing triple integral because I have to sum through all of the three variables, this quantity, which is a common basically term with them. So again, I'm going to end up with the surface integral here. Remember, this whole thing was a closed surface, so the 6 surfaces of this cube was closed. So it's going to lead us to the closed surface that encompasses the volume that we're talking about, where we carry out this calculation, this integration in here. So this was a closed surface that encloses that volume V we're talking about, and of the vector BDS, of course. Now we went to a small differential equation, and this is the triple integral over the same volume of this divergence of the vector B. A reminder over the volume V. Okay, a reminder that the divergence is a vector itself. It's an operator, actually. It acts in Cartesian coordinates in this form. Obviously, we are defining things in Cartesian coordinates, but the expression in here doesn't care what coordinate system is. So it is true no matter what system it is. So yes, you can use Cartesian coordinates to show it, but then at the end, the expression here is independent of the coordinate system. So you can, it's a valid statement no matter which system you are using. So if you don't care about Cartesian coordinates and you would want to use polar coordinates, go for it and just find the appropriate transformations to take you from x, y, z to r theta phi, okay? Anyway, so that takes care of the divergence theorem. Hopefully, this is item 1. Item 2, we're going to follow a similar analysis, by the way. We're going to extend it a little bit because I think it's, well, go for Feynman if you want to, but I'm going to modify it a little bit because I think it's clearer in here. Okay, so in the second case, this is what we're going to do, okay? We have a path. So this is a path now, a closed path. L, okay? And of course, I'm going to divide it into small patches in here. This is dl, okay? And I have a vector b again, and I'm trying to find its path integral through this closed path L of this vector b dotted with the element of path in here. In this case, that's what the path integral in general is defined, but this is actually a special case, which is a closed path integral. Okay, so that's what we're interested in, trying to find this quantity. Again, similar to the first way, what we're going to do in here, we're going to take this path. Remember, this is in space. This is not a two-dimensional path. This is not on the x-axis and y-axis only. So I'm going to go anywhere and make a cut again and say this sum through L is probably going to be the sum through L1 and L2. So in other words, my path, which is going to go in counterclockwise in the positive direction, is going to go through L2 this way, and L1 is going to go that way. So at some point, I'm going to cross this division into opposite directions, okay? Albeit both of them are counterclockwise. Both path integrals are counterclockwise. So you always do things in the most positive way, and then whatever happens at the end to the sign happens, okay? So if you happen to find the circulation negative, that means it was all along clockwise, not counterclockwise. Anyway, so this is basically our interest. We're going to show that, again, in a similar fashion, that the path integral is the same, except it's the sum of the two. So let me explain. Take an element of the path dl, okay? Obviously, for the first path, for L1, it's pointing, it's pointing up, and for L2, it's pointing down, okay? So that's the element of surface, okay? So dl1 and so dl1 is pointing up, dl2 is pointing down, okay? The magnitude of dl1 is the same as the magnitude, oops, I'm gonna remove the vector, is the same of dl2, is the same of dl, okay? Small element, okay? I should have used deltas because I'm dealing with a finite quantity. It doesn't matter at the end. We're gonna make delta d and integrate. Okay, so the point being in here is, I know the math people are probably scratching their heads now because there is a big distinction, delta and d's, so, but we're not gonna go there, okay? We're physicists. We are allowed for this exception, okay? Anyway, so the point being in here is we're trying to find the product of the vector b again, which happened to be a vector in this region that looks like this, with both dl1 and dl2 as vectors. With vector dl1, this is the angle that the vector b makes, so I'm going to call this angle theta as before. Between the vector b and the vector dl2 is actually 180 degrees minus theta. So again, this is pi minus theta, okay? So same thing. What we're saying in here is b dl1 is the same thing as b times dl1 and dl2 and dl are all the same, cosine of the angle between them, which is theta. b dl2, on the other hand, is going to involve cosine of pi minus theta, which is a negative dl cosine of theta. The two quantities are the same, except the sign is different, therefore they cancel. Which means that if I am summing this quantity over L2, at some point I'm going to take this contribution, and if I'm summing it through L1, I'm going to take the negative of that contribution, and they would cancel out, and I end up with the sum for that of the path L here, plus the sum of the path L in there, and that is exactly the overall integral. So therefore, this integral is nothing but the sum over L1, which is a closed path, plus the sum over L2, which is also closed path. So my point being in here is, why stop there? Why can't we just go crazy with these divisions and divide it into L1 into two divisions in here, which is here, and then you go down in here and call this path in here L11, and this path in here, where you go down, so this path in here, L12, and then take this and divide it into two, where you're going to come down in here and you're going to go up, and at the end, L12 will become L121 and L122, and so on and so forth, and you go crazy with the divisions. At some point, you will arrive to a place where you can do the summations, okay? So this is the path that we're going to end up with, okay? It has to be a closed path, so we have to have our starting point is the same, our ending point. So we'll start at x, y, z, and we move in the positive direction by delta x of the y-axis, and we move in the positive direction of the y-axis by an amount delta y, and we move in the positive direction of the z-axis by delta z. So this is going to be x plus delta x, y plus delta y, and z plus delta z. And of course, we're going to go down in the opposite direction now in the x-axis by an amount of delta x. So delta x drops to x, y plus delta y, and z plus delta z. And we come down by an amount of delta y. So now we're at x, y, and z plus delta z. And we close our path by going back to the origin in here where we were at x, y, z. Okay, this is my closed path, and it's counterclockwise, as you can clearly see. Everything is good, and we are coming down in here. Here is the kicker though. If I do this, and if I look at it from one projection, for example, if I look at it in here, this is my view, okay, this is my angle. If I look at it through the z direction, obviously this in and out, they don't count, they look like just so. Basically it looks like I went from the x direction, went up, then whatever happened in here, I don't see it, so it went back this way and it came down. So it looks like this, it looks like it's a motion as far as the x direction, looks like this. So we went from x, y, and z. Z is in and out of the screen, so we don't see it at all. So we're not gonna write it down. So it's gonna be x plus delta x, y, and then we went to x plus delta x, y plus delta y, and then we went back to x, y plus delta y, and back to where we started from. So this is how it looks like when I project it in here. Let me try to do an illustration of this using GeoGebra. Okay, hopefully it's gonna help visualize. So I pulled GeoGebra and I put it already in 3D mode. So I'm gonna, first of all, I'm gonna define the origin as 0, 0, 0. Oh man, I should have called it O. Okay, so the point O. The point A, I'm gonna call it 1, 0, 0. It's marking them as you can clearly see them. I know probably it's small, but you can follow. B is coordinates 1, 1, 0. That's my path, okay? I'm following the X, now the Y. I'm gonna do the Z now, ABC. So C is 1, 1, 1. And then note that the x-axis is the red one, the y-axis is the green one, and the z-axis is the blue one in GeoGebra. C. Now D is 0, 1, 1, and E is going to be 0, 0, 1. Okay, and back to the origin. So basically, this is the path, and I need to probably make this shape bigger. And let's stop at 3 on the x-axis, and let's, oops, I want to do the same thing for the x-axis, the y-axis, I'm sorry. Let's stop at 3 also, and let's do the same thing in here, and let's stop at 3. So basically, so that you can see clearly my points in here in space, okay? So again, it's oriented pointing in, so that's why you see the point C is inside, and the point B is inside, the point D is inside. I can probably rotate this, can't I? Okay, good. This is, except that, okay, so now looks like this is the points. Okay, let me draw the vectors quickly. So the vector from the origin to the A, that's this vector. The vector from A to B, that's the second vector. The vector from B to C, that's the third vector. The vector from C to D, I think that's the name I gave. The vector from D to E, and finally the vector from E to O, to the origin. Okay, so we have the path in here. Let me tell you what I'm talking about in here. If I look at it from the Z direction, it looks like, so I have the Z pointing towards me in here. It looks like basically I have a counterclockwise. The red one is the x-axis, by the way. It looks like I just described a path in there. Of course, if I look at it from the x direction, and the x direction is pointing toward me, again, it looks like it's a counterclockwise path through the YZ plane. Again, if I look at it from the y direction, again, it's going to be the same thing. It's supposed to be, actually, I'm looking at it in the opposite direction, probably. The x-axis is pointing in the wrong direction. Anyway, so I probably should reorient it. But the point being in here is it should be all counterclockwise in all directions in there, okay? If I can find, because I have my x-axis is oriented in the opposite direction, what I should really do. So maybe if I rearrange it, I think it's dizzying. I'm getting dizzy in here, okay? Okay, still pointing in that direction. Why? Okay, I want the x-axis to be oriented this way. Okay. Okay, good. Now it looks also like I'm doing this counterclockwise on the xz plane. So however you project it, however you look at it, however you look at this path, which is a closed path, it's going to look like that you're doing a square basically of dimensions delta, delta, delta on those regions. Of course, I took it square. It could be, if delta x is bigger than delta y, it could be, okay? But my point being in here is that the projection on the x-axis would look like this. The projection on the y-axis, I'm sorry, this is the projection on the z-axis. So you're looking at it from the z-axis. You're looking at it from this direction. This is how the area is. And the area is an oriented quantity, by the way. So it's pointing in the z direction by this amount. So the size of the area actually, delta A in here, let me pull my pen again. So the size of the area in here, if I can find it, where did I put it? The size of the area in this case is exactly delta x times delta y. And it's pointing in the k hat direction, pointing outside of the screen using the right hand rule. So the area is a vector quantity. Okay, so let's find what this value in the x component. So basically what we're trying to find in here is b times dl, okay, projected in the k hat direction, in k hat. So this is in the k hat. Remember, I'm looking at it through the k hat direction. So when I project it in the k hat, it looks like this, okay? So obviously, I have, through this path, I only have the x component because this is I hat, remember? So I have bx times the size of the path in this case, which is delta x, okay? And this is evaluated anywhere where really the focus in here is on y, because the x shifts from x to x, so it doesn't change. The x plus delta x shifts to it, but the y changes when I'm going from here and in here. So there is a difference in here, okay? So I'm gonna leave it as b times delta x, that's the path on this side, the x component. When I'm going up, I'm going to pick up the value of by. Again, this is evaluated at x and y, okay? And this one is evaluated for the by, when it's positive, it's evaluated at the shifted value for delta x. So this is evaluated at x plus delta x and y. Remember, now x plus delta x is the same throughout the entire path in here. Yes, y is changing, and that's why I'm multiplying it by delta y. Okay? That's the path, the length of the path. And here, by is the same because I'm assuming deltas are small enough so that the b doesn't change that much. Okay? Obviously, at some point we're going to take dx, delta x goes to 0, so practically it's going to be the value at that point. So we have this too. But now, note that this path in here points in the negative I hat direction. This path points this way, and the vector b has this component. So I have a minus bx evaluated at the shifted value for y, because y has gone from y to y plus delta y everywhere on this line. So it's going to be x and y plus delta y times the width of the length of the path, which is delta x. This size is delta x, and minus again because this path is going down, whereas the j hat is pointing up. So it's going to be a minus again. B, again, the y component, because we are in the y direction now, of the value of by evaluated in anywhere in here where x stays the same. Delta y changes, and that's why we have to multiply by it, okay? Y changes by delta y, and again, it's going to go at infinitesimal. So x and y are these points in here. Look at these two differences in here. This is, again, I'm going to pull a minus delta x as a common factor in here. So I have a minus something times delta x, and that something is the difference between these two quantities of the vector bx, the component bx at y plus delta y and bx, and that is the partial of bx with respect to y. Y is the variable in here that has changed. And in here, it's going to be straight out the sum after I take delta y as a, so it's going to be a positive delta y again. And of course, I have to come up with, because delta y is part of the definition in here of the, remember, the Taylor in this case, it's going to pick up a delta again. Let me show you the Taylor that we have used in here. It's the same thing. So f of x plus delta x yz is f of x yz plus the differential of f with respect to x times delta of that variable. Except in here, the variable that has changed is y. So that's why we have to multiply by delta y. Same thing in here. The variable that has changed is delta x, so we need to pick up delta x in here. And again, by at x plus delta x minus by, that is the partial of by with respect to x. Obviously, delta y and delta x are the same, so they're delta x times delta x times delta y. So we're going to take delta x times delta y. And what we're left with are the following quantities: the derivative of by with respect to x minus the derivative of bx with respect to y. And this is the z component. This is the zth component of the curl of the vector b. Let me remind you of what the curl of the vector b look like. The vector of the curl b is simply in the determinant format, I hat, j hat, k hat. The operator delta, nabla, it looks like this. It's called nabla, by the way, so you didn't hear it wrong. The gradient operator, and the vector bx, by, bz. So what we're looking at in here, we're looking at the partial of by, this two, with respect to x, and this is the term, minus the partial of bx, here it is, with respect to by. So we're looking at the kth component of this curl product. So this is the kth component. And so is this area too. It's the kth component of the area. So this area in here is actually pointing in the kth direction. Okay, it's pointing in the, coming out of the screen. So that's the size of the area, okay? If I project it in any other direction, let's say, for example, I'm looking at it in the xz plane. It doesn't matter. So this is the xz plane. So the x-axis, remember, the xz plane is the one in the bottom, okay? So this is how the path would look like. So this size would be delta x. We go from xz, to x z plus delta z. And obviously I'm looking at it from the y direction. So this is the y direction now. So the area size is going to be in the y direction. So the area of depth delta z, the size of the area is going to be k hat actually. So it's going to be, I'm sorry, yeah, j hat times the size of the area, which is delta x delta z. So we're going to pick up the y component now of that curve. Obviously, this will go to x plus delta x and z plus delta z. And y stays the same. We're on the same plane. So that's why I'm not writing it. Still three variable functions, so that you know. And this is x plus delta x and z, okay? Obviously, we're going to go counterclockwise. So this is probably how the projection look like. I mean, we looked at it through GeoGebra, and that's going to be valid statement. Again, at this point in here, z shifts by an amount of delta z. And the value of the function in here is in the k hat direction. And here, we're going to go in the negative k hat direction. And here, we're in the positive I hat direction. And in here, we're in the negative I hat direction. So the length of the path in here is delta z. And this should be multiplied by the difference between the two quantities, namely bz evaluated at x, y, z, I mean z plus delta z, minus, is it going to be a minus or not? Let me make sure I have the, let me make sure I have this statement correct, okay? I have this statement correct, okay? So, on this side, so we're dealing with the component bz is true, okay? And it's bz evaluated, so it's bz evaluated at, so in this case, x and z plus delta z, and x and z, so the x is shifted when we go from here to here, okay? So that's the only thing that we need to be keep tabbing. So the x changes from x to plus delta x, and the z stays the same. So this is b, I'm going to put it xz, because whatever value of xz is the same on the other side too, times the length of the path delta z, because again, I'm picking up the k hat component. The same thing in here, which is minus bz. Again, the x is shifted by an amount of x plus delta x. So whatever x was is now x plus delta x. Z, whatever was, it is the same. X is shifted by an amount. Z did not. Okay? So you have to pay attention here. So in here, it's x plus delta x and z times, again, delta z. Whew. That's this part. Okay? We still have the x component. Okay? In this direction, z has been shifted by z plus delta z, and it's the positive one. So it's positive. The x component now of the vector, because we are along the I hat direction. So this is the x component shifted in the z component. So in other words, whatever z was here, it's z plus delta z. Whatever z was here, it's z plus delta z. X, whatever is here, is the same x. Whatever x in here is the same x. At some point, we're going to take delta x to be 0, so it's going to be the exact value in this point anyway. But the difference matters. That's why we're picking up these differences. Times the length of the path is delta x. Minus bx, again, evaluated at x, z times delta x. Minus this contribution in here from this side in here, because the vector, the path in here is in the negative direction, and the vector b is the bx component. So it's the bx component, but again, x is this whole direction in here, okay? So it doesn't matter if you pick it up in here or in here, because delta x is going to go to 0, except, I'm sorry, so the delta z's are going to go to 0, so that's why we really are not too concerned about them in this direction here, okay? Okay, again, I think there is a good argument for it in Feynman. Hopefully you guys can look at it again. I'm going to pick up the delta z in here, and I'm going to use the minus again. So it's going to be a minus open parentheses. So I have a delta z in here, which is a common factor. And I have a bz evaluated at x plus delta x, and z minus a bz evaluated there. So that's going to be the partial of bz with respect to x, because x is the one that varies, times delta x. Again, plus, this is bx now, which is the open parentheses, times delta x out. So it's the partial of bx with respect to z is the one that has changed. Of course, times the amount delta z. Okay, delta z is inside the parentheses. Delta x, delta z is the size of this area. So we're going to pull it out. Times the difference between the partial of bx with respect to z minus the derivative of bz with respect to x. Again, this looks like I'm picking up the y component of the cross product, because the y component of the cross product, there is a minus in here that flips the order. So it's going to be the derivative with respect to z of bx, the derivative with respect to z of bx, minus the derivative with respect to x of bz, minus the derivative with respect to x of bz. Okay, exactly how the cross product is. The last term is going to be identical. So at the end of the day, this is how this looks like. This whole business started trying to compute this quantity. What is it? BDL. Okay, through this whole path, and it divided into two so far. You can do the rest for you guys. B times delta L through this path and here is going to be the cross product of B with the curl, basically the curl of B in the x direction times the size of the area, which is in the x direction, plus, I didn't do the x, did I? No, I did not do the x component, so you're going to finish that for yourself. But I did the y and the z component, okay? So this is the y times the size of the area in the y direction, plus the cross product of b with, in the z direction, times delta s of z. Remember, this is in space, where delta sx is going to be equal to, so this quantity, if you're curious about it, it's delta y, delta z. Delta sy is delta x, delta z. Delta, it's that quantity, that's delta x, delta z, that's the y component, okay, of the area. Again, it's pointing in the y direction. Its size is delta x, delta z. It's on that plane, okay? This area is delta x, delta y. Okay, again, from the z direction, you're looking at the xy plane, and in the patch of the area, it's going to be delta x, delta y on the xy plane. So that's basically what that is. So at the end of the day, this whole thing looked like this. The cross product of the vector, the curl of the vector b times the size of the area as just a dot product, normal dot product, everyday normal dot product, okay? And this path integral, after I take the limits when delta x, delta y, delta z equal to 0, and sum through all of these quantities, I'm going to end up with a path integral through that closed path, by the way, L, and of BDL is the same thing as the surface integral that is enclosed by that that curl of the vector B, ds, okay? And this surface in here is enclosed by, so this L in here is the one that encloses that surface, okay? So as you go from the small volume and going and growing and growing and growing, you're going to get at some point to the path that encounters it, and you go no more, okay? So this is the curl theorem, okay, that we're going to use in our, so this checks the second one. Okay, let's go to physics, okay? This is too much of a visualization and things like that. We know Gauss's law. It says that the curl, not the curl, the divergence of the electric, now before we get in there, so we have the flux of the electric field over a closed surface is equal to the sum of all the charges divided by epsilon naught. We're doing this one in vacuum, okay? In another medium, we just tune the value of epsilon naught to the correct medium. Okay, well, we know what this integral is. It's the same thing as the triple integral of the divergence of the vector vector E over the volume, so this is dv, over the volume that encloses that surface, and this is true no matter what. So this statement is true no matter what the volume is. So no matter what the boundaries of integration, these two quantities are the same, which means that the integrands are the same. Okay, we just use the divergence theorem to convert this integral into a triple integral. So then what you can say from here, you conclude that the divergence of the electric field is nothing but the charge distribution, rho divided by epsilon naught. So you go from an integral form to a differential form, which is easier to work with. Okay, and I'm going to give you a hint again for physics, basically the first time physics, electricity and magnetism course. You really don't go crazy with this XYZ business, because it's going to be very hard to work with it. Even in Cartesian coordinate, it doesn't matter what system is. So you really have to simplify the problem a little bit. Okay, and I'm going to tell you about that shortly. The other law, for example, is Faraday-Lenz law that says that the circulation of the E, basically the EMF, is equal to minus the rate at which the flux changes over a surface in here that is enclosed by that path. Okay, so of B dA. Well, we know how to work with the curl theorem. So basically what we can do in here, we can convert this one to the integral over the same surface of the curl of E over that same surface A, dA, okay? And this must be equal to minus the derivative with respect to time of this integral again of B dA. This statement is true no matter what the surface S is, which means that the integrands are the same. The only thing to pay attention to, if you take the derivative inside the integral, that the vector B depends. So the B in this case is the magnetic field, not our arbitrary vector V. So this is the magnetic field, and this is the electric field. So in this case, B is a function of x, y, z, and t. So when I'm taking the derivative of the vector itself, here, of course, after I integrate, I only will be left with the time-dependent function, because I am eliminating all the x, y's, and z's. So that's why the derivative here is the standard derivative that is written. But if I'm taking the derivative inside the integral, then I have to convert that derivative into partial derivative, okay? So the point being in here is that at the end of the day, the curl of E will be equal to minus the partial derivative with respect to time of the vector B itself. So this is the same thing as Faraday-Lenz law using this curl theorem in here, okay? So instead of working with integral equations, trying to solve them, we work with differential equations. Let me tell you a major simplification, at least for this introductory course in physics. First of all, we're not going to take any electromagnetic wave. We're going to take one that is polarized. That means the electric field from the get-go points in a specific direction. And let's, for the sake of simplicity, we take it in the x direction. Okay, so we know which direction the electric field is pointing, number one. Number two, we're gonna also make an assumption in here that the only variable in this case, that the electric field, the electromagnetic wave moves in a specific direction. And let's take that to be the y direction. So in other words, the electric component that remains is only a function of a y in force time, okay? So the problem has been reduced from x, y, z components to just one component, which is the x component, and from x, y, z, and t variables down to just yt, okay? So this is a polarized beam of light into the direction, the x direction, moving in the y direction. Furthermore, you can show using Maxwell's equation, then in this case, as a result of this, the magnetic field will turn out to be, only has a z component. So B itself also reduces to a simple form, which is also dependent on y and t. So the equations reduce a lot in complexity and become a lot easier to work with, and it's going to look like exactly a wave on a string, okay, from physics 1, from the introductory, from the first class of calculus for physics. So you can see that it is identical to that wave equation, or the sound equation also, for the pressure or the density of air, and it's going to be identical and from there you're going to pull the speed of light. Obviously, I have an epsilon naught in here in vacuum, and if I look at Maxwell's law, there is a mu naught that comes in, and the combination of mu naught and epsilon naught will give me the speed of light. So again, the purpose of this is to guys so that you are not too unfamiliar. At least I'll tell you a personal experience. When I took this class in physics, it scared me so much when I looked at these expressions. I'll be honest with you. I tried to understand where they came from, especially the curl one. Okay? I had some sort of an intuition about the divergence theorem, but not as much for the curl theorem. Okay. And the physics instructor at that time, he deferred the discussion to math. He said, "You'll learn this in math. Don't worry about it." When time came to the math class, and I was really looking forward to that, the math instructor started to give us arguments based on the flux of the electric field and the divergence and the curling of the magnetic field, stuff that we learned in physics. Well, I still want to know the proof for that. Okay. Well, I did not get the proof. I was frustrated. And at the end of the day, it took me a long, long time until I was well after my graduate school, by the way. So I must admit it. When I saw actually even though I read some part of it in Feynman, honestly, I did not see, especially the part of the curl, as clear as until later on when I further dug into it and found it. There is a higher dimensional version of this theorem that can be used, but we're not going to really go into them. We probably are not going to use them at all. So this is useful for us. Hopefully you guys have paid attention to this thing. If not, please send in questions. And at the end of the day, honestly, in our class, I'm going to do exactly what my physics instructor says. That, look, it is a divergence theorem, we're going to use it. Refer to math or to this video, okay? And here is the curl theorem. We're going to use it. And again, refer to math or to this video. Hopefully it's helpful. Go and look for Feynman, and hopefully you convince yourself as this is true statement. Now, if you're going to major in physics and you're not an engineer, you really need to know where this proof came from. You really need to know the essence of it, at least the physics version of it, because you're going to need it. You're going to need not just the theorems as a statement, but rather as how it works too, okay? Because you will be dealing with complicated scenarios that you really need to go back to the foundations. Thank you.